Hmm. Why does it do that? Okay, good. Back to the whiteboard. Okay, so this is the obvious question, is how does the scalar and the vector line integrals change? So we are doing the following: reparameterization of a path and its effect on line integrals. Just to cover the part I haven't recorded. So once again, so there are several ways to parameterize the path, and we want to know how the scalar and the vector line integrals change with respect to different parameterizations. Okay, so this is the first topic. Now, let's do this step by step. The first thing is, what is a parameterization of a curve? So the definition is a little bit technical. So let xt be a curve, be a path, sorry. Now, another function, if you want continuous, yt from a different interval cd to Rn is called a reparameter. I can hear an echo. Is somebody's microphone open? Just a second. Seems not. Maybe it's my microphone. But everybody can hear me clearly? Okay, good. So where are we? Yeah, so another function from a different interval c comma d to Rn is called a reparametrization if the following is satisfied. If there is a one-to-one continuously differentiable function f from this interval CD to the first interval AB such that the inverse from AB to CD is also continuously differentiable. And you can write yt as a composition. So yt should be written as x of ft. Okay, so then we call yt as a reparametrization of the path xt. Okay, so this is a slightly technical condition. The technical condition comes from the function f. Okay, so you need this function to be continuously differentiable one-to-one. And not only that, the inverse should also be continuously differentiable. Okay, so now once you have this reparametrization, now you want to know how it affects the integrals. Just as an example to keep in mind, so let xt be the following function. 1 plus 2t, 2 minus t, 3 plus t, 3 plus 3t, let's say. Well, 3 plus t won't harm, but just to keep parity with the lecture note. So t varies from 0 to 1. So this traces the line segment from 1, 2, 3 to 3, 1, 6. Okay, so this is a straight line from this point to, so 1, 2, 3 to 3, 1, 6. Now, if you take this function yt equals 1 plus 2t square, 2 minus t square, and 3 plus 3t square. So instead of t, you're squaring it. So this also parametrizes the same line with f from, and in case of yt also, you have the interval from 0 to 1. So 0 varies from, t varies from 0 to 1. So you need a function. So this is given by f of t, the obvious choice, equals t squared. Okay, so then you can write yt equals x of f of t. Okay, so yt is a, so yt is a reparametrization of xt. Now to the main point about integrals. So the first thing is how does it affect the scalar line integrals? And I will give you a fact without proving the fact. And as you can guess, so what do you think, so how do you think the scalar line integrals will change with reparametrizing the same curve? So think about physically what a scalar line integral gives. It gives you the mass of a body or the mass of something, right? So if you reparametrize this curve xt to another, this path xt to another path yt, do you think that the mass of a body or this sort of physical entities, they really matter or they really vary with the reparametrization? Exactly. So the scalar, so the correct statement will be that the scalar line integral will not change. Yes, so as some of you have answered already. So let me state this as a fact. So let xt we need some technical conditions. So xt is a piecewise continuous, continuously differentiable path, and f, well, and f from Rn to R be a scalar field. Okay. Then for any reparametrization, oops, of xt, okay, we get the following, that the scalar line integral f ds, so this is integral from c to d, f of y t, just following the definition, y prime dt. Now, here's where the change of variable formula for Riemann integration comes into picture. So if you recall the change of variable formula for Riemann integration, you can apply that to see that this particular integral here, this one is exactly equal to what you get if you integrate from a to b the function f of xt norm of x prime t dt. So this follows from change of variable of Riemann integration. Okay, and this by definition, so this is by definition, so this is equal to the scalar line integral along xt of the same function. Okay, so the scalar line integral doesn't change. Now, before going to vector line integrals, and as you can guess that if the scalar line integral doesn't change, I mean the vector line integral, it denotes the work done, right? So the work done has to have a sign according as you move a particle from position A to B, or you move the same particle from position B to position A. So the signs will change, right? And that's exactly what happens for the vector line integral. But before that, we have to define something called the orientation of a path. And I will only give you the informal definition rather than the technical one. So given a path, once again, suppose you have this path xt from AB to Rn. So I'm doing the most general case. Then there is a direction attached to it in the sense that we can, not we, let's say a particle can move either from xa to xb or the other way around. That is from xb to xa. Okay. Now, accordingly, we give this path an orientation. So this choice, so the orientation of xt is this choice which we have to make. Now, one important thing about this choice or the orientation is that once you choose an orientation for a particular path, you have to follow the same orientation for any other paths in Rn. So for example, if you, let's say if you travel from xa to xb for one path, then for any other path which starts at xa and xb, you have to follow the same orientation. So it should start from xa and end at xb. So something like this. So suppose you have xa and then this is xb. So we choose to start at xa and end at xb. Then if you have another path here going from, so let's say the endpoints are xa and xb, then you have to follow the same pattern. It should start from xa and end at xb. Okay, so this is what we call, this is what we mean when we say that you choose and fix an orientation, one particular orientation. Okay, we will come back to it a little bit more formally when we do, hopefully we will do Green's theorem later. But anyway, so this choice, this particular choice is called orientation. Once again, let's keep an example in mind. So, I mean, it's a special kind, to give you a little bit more precise definition. It's a reparametrization. So orientation is in some sense a reparametrization of the curve, which gives a sense of r direction to that curve. Okay, so that's a little bit more formal definition. So let's see this example. So xt, suppose this is given by this function, and t varies between 0 and 1. Now, if you draw the picture in R2, so this is from 0, 1 to R2, then it defines a line segment which starts at 0, 1. So at t equals 0, it's at 0, 1, and then travels to 1, 0. Okay, so it gives an orientation. So the starting from 0, 1 and ending at 1, 0 is one orientation. But for the same line segment, you can define yt to be 1 minus t comma t. So it's a reparametrization. So 0 less than or equal to t less than or equal to 1. So this is also a path defining the same line segment. But now you will see that the starting and the end points have changed. So here we are starting at 1, 0. At t equals 0, it's 1, 0. And we are traveling to 0, 1. Okay. So this is the point. If we use this path, we use this path once and for all. So we fix this orientation. Or if we fix this path, we fix it once and for all and use it at every example, or we use it for any vector field. Okay, so we don't change the orientation according to the vector fields. We choose and fix the orientation and then work with the vector fields. Okay, so this is an informal study of orientation. Now, here is this information about reparametrization. So I'm just reading what is written here. So we say that a reparametrization of a path is orientation preserving if it does not change the way the path is traversed. Okay, so if you look at this, so this, let's call this xt, this yt, and this, let's say, zt. So here, each one of xt, yt, and zt have the same orientation. So each starts at xa and ends at xb. So you can say that this reparametrizations yt and zt, let's say yt and z, this is not a very good drawing. Let's go to a different drawing. Suppose this is xt, xa, and this is xb. This is xt, and then I have to draw the same path yt So we call a reparametrization YT to be orientation preserving if it starts and ends at the same point as that of the original path. So YT also starts at XA and ends at XB, and it follows the same path, so same direction in some sense. So then we call, so if it does not change the way the original path is traversed, then we call the reparametrization orientation preserving. Otherwise, we call it orientation reversing. So in this particular example, YT is an orientation reversing reparametrization of XT. So it changes the direction of traversing the path. Okay, so once again, all of these are not really mathematically precise, but all you need to do is to understand what's going on. Okay, so now we can state the main result here. So this is the main fact. Let f from, where did I choose? Yeah. Be a vector field, and xt be a path, and yt be its reparametrization. Okay, so we have these informations. Then there are two cases. Number one, if yt is orientation preserving, then as you can expect, the vector line integral along this reparametrization yt is exactly same as that along xt, since the orientation has been preserved. And the second situation is the other case. So if yt is orientation reversing, then as expected, there is a change of sign. That's all there is. So minus of xt fds. Okay, so the absolute value doesn't change, of course, because if you consider work to be a vector quantity, the absolute value won't change, if, I mean, irrespective of the parametrization. But since it's a vector, there should be a change of sign according as you take orientation reversing or orientation preserving reparametrization. Okay, so that's more or less everything that you need to know about line integrals. So any questions about this part? Anything that you are not clear? So the main thing is to understand about what's going on in the vector line integral. For scalar line integrals, nothing changes. But for vector line integrals, there's a sign to be taken care of. So understand this informal definition of orientation. That should be good enough. And then understand how it affects the vector line integral. Okay, so in the lecture note, you will see one problem which is not really about this reparametrization, but so this is the problem. So there is a vector field given. So this is we are at page 5. So more or less at the end of page 5. So you will see this problem that you have a vector field. So f of x, y, z is given by x comma minus y comma x plus y plus z. And then I proceed to compute the work done. But work done in moving a particle along the path y equals 3x squared, so a parabola, and z equals 0 from the origin to 2 comma 12 comma 0. Now, if you look at the example, everything is straightforward. You just figure out the vector line integral as you should, just following the definition. In the answer, you will find a negative sign. So you will find that the answer is minus 70. So what does it mean? So you'll see that the integral is taken from 0 to 2. Yeah, the integral is of course from 0 to 2 because the interval is from 0 to 2. Now, what does this minus sign reveal? The minus sign actually reveals that the particle travels other way around. So it travels from 2 comma 12 comma 0 to the origin, not the other way around. So if you reparameterize xt accordingly, then you will get a plus 70, for example. So that will reflect the fact that your reparameterization starts at this point 2 comma 12 comma 0 and ends at 0 comma 0 comma 0. So look at this example, and the main thing is why this negative sign comes, and I explained it that the minus sign signifies that the particle was actually moved from 2 comma 12 comma 0 to the origin. Okay, so that's more or less about line integrals. We move to multiple integration right now, and mostly we will stick to double integration. So this will be the next topic, multiple integration, but mostly double integration. Because at the end, we want to relate the line integral to the double integral. So that would be the Green's theorem. Anyway, once again, for multiple integration, if you look at the lecture note, so lecture note 5 from page 7 onwards, so VC5, so page 7 onward deals with multiple integration. And there is a theoretical part of it, and it's explained throughout lecture 6 and from page 7 to 10 of lecture 5. And what I plan to do is to go through, once again, like the Riemann integration part, what I will do is go through this section fast, leaving the details for you to read, and I will just point out to some important properties which we will need. And then we will move as quickly as possible to the computations of double integrals. So are you happy with this approach, or if you want, I can explain a little bit more. So I can go a bit more slowly, but the trade-off then would be that maybe we have to leave out Green's theorem. So whatever you want, I can do both. Go slowly, okay. So you want me to cover more or less the theory of multiple integration and double integration. Okay, so then, okay, so let's do that then. So well, in any case, I have to go reasonably fast, not too slow. So the basic idea is that we want to generalize Riemann integration to Rn. Okay. Now, what does Riemann integration say? Riemann integration says that you have a function, nice enough function, from a, b to r. Let's say continuous function, just so that you can draw a picture. So for Riemann integration, so this is f, let's say this is a and this is b, this is f of a and this is f of b. So Riemann integration computes this area under the curve, right? So integral f, let's say dt from a to b, computes the area of the shaded region. Okay. Now we want to do something similar for, rather, well, it should be a comma fa and b comma fb. Now we want to do something similar for multiple integration. Now let's stick to R2 so that we can draw pictures. So we will stick to R2 so that but keep in mind that the same idea holds for Rn. So for n greater than or equal to 2. So what we do is, how do we integrate a function f, let's say, which is defined from this R. So R is a comma b cross c comma d. So this is a rectangle. So it's a product of two intervals, 2r. Okay, so how does one do that? So we have this, let me draw it in this way. So this is so this is the rectangle AB cross CD. Okay. Now this function, if you draw the graph in a similar manner, this function will give you a three-dimensional picture. Let me. So then, see. Okay, so you have a three-dimensional picture. So this is f of xy. So my drawing is not up to the mark. Okay, and then you have a volume under this surface, right? So then the whatever integral, so whatever integral this of f we want to compute, should give us the volume. Okay, so with this in mind, let's try to do step by step. Now, okay, so once again, sticking to R2, let me call it the first method, first approach. So let f be defined from a rectangle. So this is a comma b cross c comma d to R2 be continuous. So we need this fact, need this restrictions rather, be continuous and non-negative. Okay. Then the volume is computed by the integral or the repeated integral I given by, so you first integrate along this interval c comma d, treating fx comma y just as a function of y. So then integrate along dy, and whatever be the result, since you plug in c and d, you get a function completely depending on x. So now you can integrate along x. Okay, and then it's a fact, because f is non-negative and continuous, that if you switch the order of integration, so now you first integrate along a comma b, treating fxy completely as a function of x, and then plugging in the constants a and b, and then integrating along y. And the fact is that these two integrals give you the same, or these two are the same numbers if f is non-negative and continuous. And this number, whatever this number is, gives you the volume of the area, rather the volume under this surface. Okay, so at least if you have a nice enough subset of R2, namely if you have a rectangle in R2. Oh, just a moment. So this is from this rectangle to R, and if you have a function from this rectangle to R with this nice properties, then the volume is computed by computing these two Riemann integrations basically. So there's nothing new, almost nothing new, just that you have to compute twice. So as an example, let's see one computation. So find the volume under the graph of fxy equals cosine x and sine of y over this rectangle. Okay, so just following the definition, this I is given by, so now I first integrate along 0 to pi by 4, so pi by 2, then 0 to pi over 4, cosine of x, sine of y, dy dx. So integrate with respect to y and then with respect to x. And each of these integrals are fairly simple. So this is my minus 0 to pi over 2 minus cosine x cosine y. Now you evaluate at the endpoint 0 to pi over 4, dx. Okay, so this is equal to the following. So 0 to pi over 2 minus root 2 over 2 cosine of x minus cosine of x dx, and then evaluating each integral, the final answer is given by 2 minus root 2 over 2. Okay, now check that if you flip the integrals, it will give you the same answer. So either by directly checking it, so directly computing it, or maybe by some change of variable formula, but try to check it, that it gives you the same formula, same number. Okay, so this is the basic part. Now moving on to VC6. So we are in lecture 6, so we'll start lecture 6 right now. The general theory. Okay. So what we do is the following. Now, still we stick to rectangle. So R is a rectangle. And F is a function which is, let's see what we have taken. So just a function, and F from R to R, a function. Okay. So this is the part which I am going to skip the details. The thing is that much like the Riemann integration, what you can do, so you have this rectangle, right? Now, if you know Riemann integration, what you do is to partition the line interval, right, for Riemann integration. So you have this line, then you partition this line integrals. So this is for Riemann integration. Now, what you do here is something similar, but since this is a two-dimensional structure, you partition this in two directions. So you partition this rectangle into tiny square boxes, tiny squares rather, okay? So call each of these small boxes Rij, and then, so Rij's, for example, if you look at the lecture notes, so Rij is given by xi minus 1 comma xi cross yj minus 1 cross, yj minus 1 comma yj, where xi, so where this x naught up to, I think, xn is a partition for the interval AB, and similarly y naught up to yn is a partition for CD. So you take the product of the two partitions to get a partition of this rectangle, and then much like Riemann integration, you define the Riemann sum of this partition, Riemann sum related to partition, and then you take the limit of this Riemann sum, and then if the limit exists, you call that limit to be the double integral. So you take, so we take the double, we take the limit of the Riemann sum in this case. So IF, so this is the notation I have used. Rather, no, sorry. Riemann sum S F. So P denotes the partition and Cij denotes the point inside this tiny squares. Okay, so this is defined by taking this sum I from 1 to n. So evaluate f at this point Cij and take, so Aij denotes the area of this tiny rectangle. So this delta Aij is the area of Rij. Okay, now call If to be the limit as the norm of this partition tends to 0 of this Riemann sum. So if If exists, we call it to be the double integral. Okay, so this is more or less an informal idea of how to define the double integral. So we use the following notation. So either we use the following integral on this R f of dA, or we also use the following R f dx dy. Although we have to make sense what this dx dy means. Now, once again, we have a few facts to make our life easier. So the first fact is that if f is continuous, so if f is continuous on the rectangle, then if exists. So f is double integrable in that case. And number two is the following. A function, so this is a stronger condition, a function f from R to real number is double integrable. So it's an if and only if condition. So if and only if f is bounded on the rectangle, so that is the modulus of fxy is less than m for each x comma y inside R, and f is continuous in R minus a set E. So this notation, so this R minus E, this means set of all points in R such that this is not in E. So where E has, I don't want to use this term, but there is no better term to say this. It has measure 0. Okay, so in R2 you can think of it like an area. So think of E having 0 area. even better, E in most cases is a finite set. Okay, so you can think of it like this, that F is double integrable if and only if. So the important part is only if. So F has to be bounded on this rectangle, and number two, F has to be continuous outside a finite set. So if these two conditions are satisfied, then F is double integrable. And it's exactly similar for the usual Riemann integration. The usual Riemann integration from interval AB to R, it has the same sort of criteria. Okay, so this is, was it too fast or is okay? Okay, so this is sort of a rapid introduction to Riemann integration. Now, Fubini's theorem, this allows us to switch the order of integration. So what Fubini's theorem tells us is, in nice enough conditions, you are allowed to switch the order. So let's write it down. So let F be double integrable on R, then so double integrable means that F is bounded and it's continuous outside of outside a finite set of points. Then you are allowed to switch the order of integration. So the double integral F dA, so this is equal to, first you can integrate along CD, and then you can integrate along AB, or you can do the other way around. So first integrate along AB and then along CD. So this switching is the key. So you are allowed to flip. Okay, so this is where you need a proof. So Fubini's theorem, the key part is this switching. So once you have this switch, well, another small part is to show that one of these two is equal to this formal definition. So that's another small part, but the main point about Fubini's theorem is this switching. Okay, so this was the nice enough case. So you have a rectangle in R2, then a function from the rectangle to real numbers, and then you can integrate if F is continuous and is bounded, continuous outside a finite set and is bounded. Now, what about more general regions which are not rectangles? I mean, for a good definition, you need something which is more general. I mean, integrating on a rectangle is fine, but not everything in R2 is a rectangle. There can be triangles, there can be weird shapes and everything. And there should be a way to generalize this notion of double integral. Okay, so the first thing we restrict is the following. So let D be a bounded region in R2. Of course, So you can think of D having a closed boundary, or even let's say you can think of D as having a finite area. Okay, so we don't want D to have infinite sort of areas. We don't want D to be too general in that sense. Okay, so we want to have a finite region, so having finite area, and it has a closed boundary. So in the sense that you can tie up D with a fence, let's say. So typically you can draw a picture like this. Okay, so this, whatever inside this closed curve is D. Okay, and the part here, little bit bold, this is called the boundary of D. So we will come back to it when we do Green's theorem, but we want D to have this sort of shape. So finite area, and is it can be bounded by a fence, let's say. Okay, so with that, so in such a D, we can define the double integral. Keep in mind that D can have some other complicated shapes. For example, same idea here, but you can have a hole in between. So this is a hole. So this is our D. Okay, or even weirder, something like this. Okay, so, and maybe a hole here, just to make life harder. So this shaded portion is our D. So D can have this weird kind of shapes, but we are good as long as it has this finite area, and you can enclose D with this boundary. Okay, so then the first thing we do, so let f from this D to R be a function which is bounded. Okay, then we define a new function in the following way. So new function, call it, just to give a name, fx of x comma y. So this is defined by, it's a simple definition. So it's f of xy if the point belongs to D, otherwise just define this to be 0. Oops. If the point is not in D. Okay, so of course, fx is bounded in all of R2 because f itself is bounded. Now here is this, what happened here? Just seems to be a page missing anyway. So, okay, so now since D is bounded, it can be enclosed. So this is the main idea. So it can be enclosed inside a rectangle. Okay, so something like this. So suppose this is D. You can capture this inside a rectangle R. Okay, and for rectangles, you know how to compute the double integral. So we define, so for the moment, this is just a definition. The double integral on D of f, let's say dA, so this is equal to, or this is by definition, the double integral along this rectangle R of this function fx of x comma y dA. Okay, if the right hand side exists. Okay, so once we have this definition, there is an obvious problem. Can you think of a potential problem with this definition? What could be, I mean, what can somebody argue against this definition? I mean, as it is, it makes perfect sense. Well, I mean, that's why I wrote that if the right hand side exists. You can suppose f to be continuous if you want. Even then, there could be a problem. Okay, so the thing is that once you are choosing a rectangle which encloses this D, your choice is not unique, right? So there could be a different rectangle. Let's say R prime, which also encloses D. And then you can play the same game. You can define the double integral along R prime of this fx dA. And suppose that this also exists. Then what guarantees that these two numbers are same, right? So there's an obvious question. If these two numbers are not same, then you cannot define one of these two as your definition, right? So for the definition, you need all such double integrals on the rectangles to agree, right? So then only you can define it to be the double integral on this region D. So it will be a meaningful definition. So otherwise it doesn't make any sense. So, and the problem persists if you just work with any function. So if you just pick up any function, then it might happen that for different choice of rectangles, you get different answers. So then there's no good way to define a double integral for the region. And that's the reason we restrict our function. So then we need the following fact. So if f from D to R from D to R is continuous and bounded. So you need continuity on all of D and boundedness, continuous and bounded on D, then the definition above does not depend on the choice. Choice of the rectangles containing D. Okay. So one remark is that this is not the most general case, but it covers all the examples that we will use. Okay. Now there are several properties of double integrals, much like the Riemann integration, and I will skip once again. So we are now on page 7 of lecture VC6. So I'll skip the obvious properties, like if you take the sum or difference of two double integrable functions. You add them, you get them to be double integrable and things like that. And I will state the most important property that we are going to use often. So I will write it as the most important property. So practical use wise of double integrals, which is the following. So this is property number 4 on page 8. So if a function is double integrable, so this is the statement, integrable on bounded regions D1 and D2. Okay, so you have two regions, D1 and D2. Then it is double integrable on their unions. Okay. Oops. Moreover, if their intersection is empty, so they have no common points, so they're disjoint, that's what it means. So they're disjoint, then we even have this nice formula that the double integral along this D1 union D2 of f is the sum. So this is much like what you did for the Riemann integration. Remember, so you broke up the path into several smaller paths, and for nice enough functions, the total integration on the whole path is the sum of the integrals on this individual paths. Here also you have this generalization. Suppose you can break up a bounded domain or a bounded region into several other smaller bounded regions, satisfying this conditions that their intersection is disjoint. Then the double integration on this whole domain can be broken up as a sum of double integrals on this individual smaller domains. So this is the generalization of this breaking up the path in several smaller paths, so to say. And this is the property we will often use when we, or well, at least we will use in some examples when we compute the double integral. So this finishes off with lecture 6. What we do in our next class is solve some problems on double integrals, and yeah, so next class will be spent mostly on solving problems in double integrals, and next Tuesday we will do a little bit on Green's theorem. So that's the plan. Okay, so that's all for today. So any questions? It's been a long class. Well, I mean, long for an online class. Where can they record it? Well, I post them on YouTube and I post the link on eCampus. That's what I'm doing. So far you haven't seen any lectures? So it's on eCampus on the announcement. So usually, not usually, so all the time I give the link on announcements. Anything else? Okay, if not, then have a nice week and see you on Thursday then. Bye-bye. Bye. Peace. Yeah. Peace to all.